viewers, welcome to CEC lectures. Myself Dr. Preeti Jagmani. I am a teacher of computer science at Aryabhat College, University of Delhi. So in this lecture series of operating system concepts, presently we are going through the module of process management, and in the previous lecture of process management, we have seen what is the process management, then what is process, how it is different from a program, and we have also seen various states of process which are new, ready, waiting, running and terminated. Now in this lecture we are going to start with the concept which is better known as PCB. PCB stands for process control block. Now process control block is an entity which is there to represent a process. So basically we can say each process in the system, whether it is in whatever state, it is being represented in operating system by a PCB, which is process control block. It is also known as a task control block, and it contains very important pieces of information about a specific process. So every process is going to have a PCB, and within that particular PCB various pieces of information are stored. Now let us see what all processes, what all informations we are going to store inside this PCB. So here you can see the structure of a process control block. So a structure of a process control block is given in the figure. It contains process state, it contains process number, it contains program counter, it is having registers, then memory limits, then list of open files. So here you can see all these information which is stored inside a process control block, as the name indicates, or as the we can see by their titles, is very crucial information about the process. So let us try to explore them one by one. So process state, when we see in the previous lecture, we have seen there are 5 states of the process: new, ready, running, waiting and terminated. So this particular process of which we are talking about, or of which we are studying the process control block of, in the which state, that is determined here, that is kept an account for here. Then there is a specific number of the process, then the process number is there written. Then we have program counter. So program counter is basically we can say it indicates the address of the next instruction to be executed for the process. So which instruction is going to be executed next, that instruction, the location of that instruction in the memory is the value of the program counter. So program counter basically indicates the address of the next instructions to be executed for the process. So after program counter, if you can see in the figure says registers. So now coming to the register. So basically here I am talking about CPU registers. These CPU registers vary in number and type depending upon the computer architecture. So each and every computer, based on their architecture, may have different types of registers, may have different number of registers, but generally we can say this include accumulator, index registers, stack pointers and general purpose registers, plus any condition code information. So all these we can say registers or all these information which is stored in index registers, accumulators, stack pointers, general purpose register, plus any condition code information is stored inside these CPU registers. So that particular process is using which all registers will be kept an account here. Then we need to also save the state information, because this state information must be saved when an interrupt occurs, and then after solving that interrupt, or more technically we can say after handling that interrupt, when a process is continued afterward, from that particular point it is going to continue onwards. So, in order to allow the process to continue correctly afterwards, after handling the interrupt, the state information must be saved. Then again it have some CPU scheduling information, that means which process is going to get a priority as far as CPU cycles are concerned, what are the pointers to scheduling queues, all those information is also kept inside PCB. Not only this CPU scheduling information and the information about the state of the process and the program counter, but the information regarding memory management is also stored here. Now, what kind of memory management information I am talking about is, it is the value of base and limit registered, and the page tables, segment tables. Now, all these information is that we will be covering in greater depth when we will be going through the module of memory management in detail. So, basically base and limit registered, page table, segment table and many other information depending upon what kind of memory system or what kind of memory management system is being used by the operating system, that all information is also saved or also I can say kept inside the process control block. Apart from that, it also have accounting information, that is amount of CPU which is required, amount of real time which is used, then total amount of CPU which is required, also the amount of CPU which it has already used for, then what are its time limits to which the CPU is being executed, some account number, jobs, processes number and so on and so forth. So, all this accounting information is also stored inside your process control. Then we have input output status information, which is we can say the list of all input output devices allocated to that particular process. Not only the input output devices, but list of open files and so on. So, all this information which includes process state, program counter, CPU registers, the CPU scheduling information, then we have memory management information, accounting information and input output status information. All those pieces of very crucial information are stored inside the process control block, which is available for each and every process. Now, why this process control block is very important, that can be understood with the that we can understand with the help of this figure. So, here we have two processes, one is process P0, another one is process P1, and operating system is handling these two processes. So, now let us see what is happening. There is an interrupt or a system call. Till that time this process P0 was under execution, and now here is an interrupt or here is a system call. So, what will happen? This process P0 will go from we can say executing state to idle state, and for this state change there we need to save the state inside the process control block. Let us say we name it as PCB 0, which takes an account of process P0. So, the state have been saved in PCB 0, and now PCB 0 state have been saved. Now, we cannot keep CPU idle. Meanwhile, we will load the state from process control block 1, which belongs to process P1, and the process P1 which was in the idle situation earlier now comes into the situation of execution, and your process P0 has gone into an idle situation. But so, basically I can say it is not executing presently. Then after some quantum of time, again there is an interrupt or system call, and this execution of P1 has been interrupted. Now as the execution has interrupted, the state has been saved in PCB1, and now here P1 is in the idle state, if you can see in the figure. After this, there is a reload of process P0, and then we again need PCP0 from which we are going to reload the state. And now after being idle for some time, your process P0 is again in the state of execution. So this is what I can say, kind of flow when the CPU is taken from one process and given to the another, or technically we can say it is a CPU switch from one process to another. So this is the diagram explaining that switch. Now coming to whether it is kind of only the two processes in which the CPU is being switched, or it is going to be a more micro level entity. So here comes the concept of threads. So whenever we are talking about this CPU switching, or we can say context switching, the discussion will not complete till we go through the threads. So basically we can say process is a program that perform a single thread of execution. So till this point, whatever we have seen, we have taken the process as, or we have considered the process as such a program which is performing a single thread of execution, or which is performing kind of in a layman or in a simple language, we can say it is performing just one task. Now a single thread of control allows the process to perform only one task at a time. Now let us consider the example of a word processor program. In a word processor program, or in any other thing, let's say word processor, the user cannot simultaneously type in and run the spell checker within the same process. Why? Because these are separate threads. So within the process or within the program of word processor, user cannot simultaneously type in and run the spell checker. So these two things cannot go on hand on the same application. These are two different threads. But if we can see some modern operating system, they have extended the concept of process to allow a process to have multiple threads of execution, and thus to perform more than one task at a time. So till this point we have seen single tasks at a time. So even if it is process 1, the CPU is kind of executing process 1, process 2 is in another state, or maybe process 2 is sitting idle or in any other different state, not in running of course. But when we talk about the threads within the system, we have seen the scenario, the threads within the system will not be allowed in the normal system, it will not be allowed to work concurrently, as I have given you the example of word processor. But in the modern operating system, this is a scenario which is possible, that to perform more than one task at a time, and this is possible because these modern operating system or these contemporary operating systems have extended the process concept to allow a process to have multiple threads of execution, and all these threads can kind of go hand on hand simultaneous at a time. Now what kind of systems are these in which we are talking about these executing threads more than one thread at a time? These are, we can say, multi-core systems in which where we can say multiple threads can run in parallel. So on a system that support threads, or on a system even that can support multiple threads, the role of PCB is even more crucial. Here the PCB is expanded to include information for each thread. So the point which I am trying to make here is, it is not that the only information which we have seen, that is CPU scheduling information, then memory management information, process state, program counter, accounting information, input output status information. But apart from that, there could be information of various threads which is to be stored on the process control blocks. So, just because of this kind of agenda, we have taken in the concept of threads here. Now, coming to, we have seen the various states of process in the previous lecture, and in this lecture till this point we have started from process control block. So, what actually a process control block is we have seen, and what kind of information this process control block is going to hold, that also we have seen. Now, coming to the scheduling of the processes. When we see the multi-programming system, the basic objective of a multi-programming system is to have some process running at all the times, because we don't want the CPU to sit idle, because the agenda is to maximize the resource utilization, and CPU is one of the most crucial resources. So, basically we want to maximize the utilization of CPU. So, in a multi-programming system, some process is running at all the times. Next, the objective of the time sharing systems, apart from the multi-programming systems, if we see the time sharing system, the objective of time sharing system is to switch the CPU among processes so frequently that the user can interact with each program while it is running. So, you can have multiple processes or multiple programs or multiple processes going on, and CPU interacts with them so frequently that user is having the impression that only one process is going on. Now, here we have an entity named as process scheduler. This process scheduler selects an available process, and this for the program execution on the CPU, and this available processes is going to be one of the processes from the set of several available ones, but that process is to be chosen from the set of ready processes, so that the CPU can take them up and this state of that particular process can switch from ready to running. For a single processor system, there will never be more than one running process. I am not talking about threads here, because thread is again a micro entity. There will never be more than one running processes. If there are more processes, the rest will have to wait until the CPU is free, and then they can be kind of taking the CPU, they can be rescheduled. So, one process inside the I can say in the running state, other ones in the either in the ready state or in the state of maybe waiting, if I am talking about a single processor system. So, even in that single processor system, we have various queues, as I have named. One queue is a ready queue. This is the queue of processes which are ready. So, let us try to explore the concept of scheduling queues. As processes enters the system, they are put into a job queue which consists of all the processes in the system. So, when your process is going to take entry, this is going to put inside a queue, which is a queue, I can say a common queue consisting of all the processes in the systems. The processes that are residing inside the main memory and that are ready, these are waiting to execute or waiting to get a CPU cycle, are kept on a list called the ready queue. So, one is a macro level job queue in which all the processes of the system are kept in. Then we have one more queue which is known as the ready queue, and that ready queue is the queue of all the processes which are residing inside the memory and are ready to catch hold of CPU. Now, this ready queue is generally stored in the form of a linked list, and this is a concept which we have already covered in the course of data structures. Now, how this linked list is implemented, let's try to visualize that. A ready queue header contains the pointers to the first and final PCBs in the list. So basically, when we say that there is a queue which is being implemented for the ready processes, so what will be the entity of the node? So each and every node will be a process control block. So there will be a process control block of job 1 which is ready, then there will be a process control block of job 2 that is also ready, and process control block of job 3 which is ready, and then so on and so forth. So the queue header consists of pointers to the first and final PCBs in the list. So this could be a circular, I can say, linked list, and each PCB includes a pointer field that points to the next PCB in the ready queue. So all these process control blocks are connected to each other using the pointers. But it is not only the ready queue. For scheduling the processes, or in order to implement the process scheduling system, the system also includes other queue. So when a process is allocated the CPU, it executes for a while and eventually quits, or it is interrupted, or it is waiting for the occurrence of a particular event, such as completion of an input output request. Anything it could be interruption, it could be occurrence of a particular event, or it could be completion of an input output request. So let's take the third scenario in which the process makes an input output request to a shared device such as disk. Now, is it the scenario that the moment it is going to make a request for a shared device, it is going to get the device? Actually not. The disk may be busy with other processes and serving the input output request of other processes. So that means this process may have to wait. So here is one more queue. Earlier it was the job queue, then it came inside the ready queue, got the CPU execution with the interruption. Now it is again admitted inside a device queue, because that device, which as an example I am taking as disk, is not free to serve that particular process. So a list of processes which is waiting for a particular input output device is called a device queue, and each device is having its own device queue. Now how this scheduling is going to happen, let us try to understand this with the help of a figure. So there is a new request for, or there is a new process, it is going to get inside the ready queue in the initials of it. Then after that it is going to get CPU. If it is done, it may get out of the system or get out of the queues, and it is in the terminated state. If not, it may raise an input output request, and in the case of an input output request, this most probably will join an input output queue, and after input output queue, if it is going to get input output device which is a resource, it will again get into the ready queue. So the first loop is clear here. So here we can see this input output and the CPU which are written inside the circles are the resources. So CPU is a resource, and so is input output devices are the resources. Another scenario could be the process is inside the ready queue, it is going to get the CPU, but its time slice expired. So let's say 20 nanoseconds are given to each and every process, because there are many other processes in the queue. So its time slice expired, but it is requiring some more amount of CPU. So it will again join the ready queue through the second loop. Coming to the third loop, which says after having some amount of CPU cycles, it is going to fork a child. It is going to generate a child process, and then that child process is going to be executed. After that, the ready queue will be joined. Or the fourth scenario could be the fourth box, which is the CPU is kind of, I can say, taken up by the process, but there is an interrupt, and now it is going to wait for an interrupt, and interrupt occurs, and after the interrupt handler it is going to go to the ready queue. So here there are four scenarios in which a CPU is a process is going to leave the CPU, whether it is going to join an input output request, input output device queue in the scenario of an input output request, or its time slice is expired, it is again going to the ready queue. It is going to generate a child in which the child will execute, then it will go to the ready queue, or it will wait for an interrupt if an interrupt handler is going to take care of that interrupt, and then again it is going to go to the ready queue. So here each rectangular box represented a queue, the ready queue, a device queue and a set of device queues, and the circle represented, as I told you, is the resources which are serving these queues, and the arrows indicates the flow of processes in the system. A new process initially put into the ready queue waits for its execution, or after its execution it may get dispatched, or it may join other queues such as ready queue or input output devices, input output device queue. So once the process is allocated the CPU and is executing, one of the several events which are shown in the figure could occur, and the process could issue an input output request and then be placed in an input output queue. Either the process could create a new child process, wait for that termination, or the process could be removed forcibly from the CPU as a result of an interrupt and could put back in the ready queue. So in the first two cases in which it is waiting for an input output device, or the time slice has been expired, the process eventually switches from the waiting queue to the ready state and is then again put back into the ready queue. And this process continues this cycle until it terminates, at which time it is removed from all the queues and has its PCB and the resources are deallocated. So here in this lecture we have first started with what is process control block, what all amount of what all kind of information it is going to store, and then we have seen that even within a single tasking system or in a single user system, how this process scheduling takes place and how these processes changes from one state to another. Here is a list of references which is being used for the preparation. So hope you had a fruitful learning. Thank you.